Hi everyone, welcome to this video, and today we'll be talking about MATLAB's application in finding gain and phase margin of a transfer function or a complicated form of transfer function. So here is a snippet of the code that we'll be using mostly in this example, and we'll be mostly focusing on how to analyze a transfer function of a complicated system or multiplication of several smaller building blocks together to find out what is the total transfer function of the system and plotting the Bode plot of that using MATLAB, as well as finding the gain margin and phase margin of that and its application in the stability of a system. So let's dive into the example really quickly. So over here, we have a bunch of systems on the right side, a system 1 to 8, that they are the transfer functions of the total system, which some of them are a multiplication of some smaller building blocks, as you can see here. And the purpose of this tutorial is to find out what would be the Bode plot of each one of them using MATLAB, as well as what would be the equivalent gain margin or phase margin of the system that we will be eventually using that to find out the stability of the system. So let's try to solve this question or each system one by one as an example. So start with the system 1. In order to start the putting down of the numbers for this system, we can break it down into smaller pieces. So for instance, the system 1 is composed of 3 individual components of 1 over s multiplied by this block, first order, and then another first order. So we can actually make use of each one of them as one system. So I would say, for instance, G could stand for one of these systems, and I would use TF as a transfer function so that I can use 2 brackets, comma, another 2 brackets. So the first 2 brackets will include the coefficients of the numerator, and in this case, as I'm going to use 1 over s, numerator has a coefficient of only 1. So we will start actually with the maximum s first, so that actually since it doesn't have any coefficient for s, we start with 0 and then would move to the constant coefficient. So essentially this would turn into 0, comma 1. We can remove the comma, and that wouldn't change the whole transfer function. In the denominator, by the way, we have s. So starting with the maximum s, so we have coefficient of 1. On the other hand, it doesn't have any constant value, so we would have 1, comma 0. So that essentially would create this transfer function. We can easily see how it turns out with Control Enter, and at the bottom of the command window, you can see that G is represented as 1 over S, and we can verify that our assumption was correct. So again, the numerator and denominator are given with coefficients starting with the maximum power of S, moving down to the lower power of S, or constant value. So essentially, we can call this, the first one is G, and the second one can be K, for instance. So let's type K as TF again, 2 brackets. The first one contains the coefficients of numerator, so we don't have any S, so that will be 0, then 0.8. So essentially, this will be 0, then 0.8. Denominator, by the way, we have 5 and 1. Starting with the maximum power of s, 5 and 1. So that will be the second. The third one could be h, for instance. The third transfer function. So again, TF, 2 brackets. The first one, numerator. So we don't have its coefficient for s. That will be 0, comma 1. Denominator, however, we have 0.5 and 1. So let's Control Enter, and actually you can double check all of those individual ones here at the bottom. 1 over s, then 0.8 divided by 5s plus 1, that's correct, and then 1 over half s plus 1, So now that we made sure that all of those individual building blocks are correct, we can then create S1, for instance, and call that with multiplication of G times K times H. So you can see that that multiplication turns into this complicated form of S. And if you want to get the Bode plot for that, we can easily use the code Bode of S1, for instance, and control enter that would give us the Bode plot of this transfer function, the complicated S1 transfer function. So as you can see here, the top graph shows the magnitude versus frequency, and the bottom one shows the phase versus frequency. And it can be further modified in terms of adding grids and all of those details. However, we just need to focus on the phase margin and gain margin. So we can manually start using the definition of the gain margin and phase margin to find out what those values are. And essentially, gain margin is where the phase hits minus 180 degrees. So the frequency of around minus 180 degrees, and finding the frequency of that value and evaluating the gain at that point, roughly minus 9. So this shows that at this frequency that my phase is minus 180 degrees, how far I'm away from the 0 dB. And in this case, I'm 9.18 dB away from 0 dBs, and that's how low actually we are from that. It means that we can still add this amount of gain to the system, and the system would still be stable. So that's how it really works. That would be around 9 volt dB of gain margin we would have. In terms of phase margin, by the way, we need to start with the magnitude plot, and then try to find out what is the magnitude of 0 dB. So we can start looking into the frequency that the magnitude has around 0 dB, and then find that frequency, in this case 0.386. So in that frequency of 0.386 this time, so I would actually remove the other ones to make it clear. So at this frequency, we can see that the phase is minus 163 degrees. We just need to find out that how high it is from minus 180. So in this case, it's around 17 degrees, roughly. That means that we have a phase margin of 17 degrees, which means that the phase could be degraded by another 17 degrees and our system could still be stable. That's how the phase margin is defined with respect to the difference from minus 180 degrees. And obviously, the gain margin should be a positive value when the gain is lower than 0 dB. Phase margin is a positive value when the phase is higher than minus 180 degrees. So these are the two constraints that we need to monitor all the time. But on the other hand, one might ask that what would be a practically decent level of gain margin and phase margin? Essentially, a good region for the gain margin is something above 6 dB. That's called a good region for a gain margin. In our case, that's 9 dB. And a good region for phase margin is around 40 degrees. In most of the practical cases. In this case, we don't have that much of good phase margin, by the way, only 17 degrees. So these are the basics of gain margin and phase margin, that how we can find out using MATLAB. However, there is a slightly better way and easier one to find out these values without going into the detail of manually picking these points one by one. And I'll show you in the next example. So over here, imagine that we don't want to use the Bode, but we use another function called margin of S1. And if we plot this, it would create not only the Bode plot, but also will calculate both gain margin and phase margin automatically. So it would do that search instead of us doing that manually. It, as you can see, has found quite closely the gain margin around 8.79 dB and a phase margin of around 17 degrees. and their corresponding frequencies are also given here. So here is a much better way to find out the gain margin and phase margin of a design, and subsequently will help you find out how much you need to further modify your circuit or transfer function in terms of adding a controller to add to the gain margin or phase margin to make it more stable. That's how it really works for this system. I would like to just do another one really quick together. For instance, if you want to start on system 4 as an example, or let's try to go for system 8. So that's how it really works for a transfer function, Bode plot, and margin assessment using MATLAB. And I will just want to make another example of, for instance, system 8 over here together to make sure that we have a better understanding of this example. So I'm actually clearing the screen and closing all the figures. Now, in this case, I have again 3 systems, starting with the first one as G, so 20 over S plus 1. So if I want to use that here, that would be again 0 and 20. S is 1 plus 1, that would be 1. So G is created. The second one, in the numerator, I have 0.8 and 1. So this would be 0.8 and 1, starting with S. In the denominator, by the way, I have a second order system, starting with, again, highest order of S. So 8, 4, and 1. So that would be 8, 4, and 1. That would constitute my system. And if I want to make sure that my numerator and denominator have the same order, I need to add a 0 to the numerator to make sure that this starts with a 0 S2. The last one, 1 over, so this would be 1 over half S plus 1. So this is exactly half S plus 1. So if I want to make sure that all of those blocks are given as I'm expecting, you can see that 20 over S plus 1, point S plus 8 over S squared plus 4S plus 1, and also the last one are all given correctly. And the response of the system right now is plotted as you can see here. So this looks like to have a gain margin of -7 dB and a phase margin of -18 degree. These are also valid numbers, since in this case you can see that for the gain margin, the frequency at which the phase becomes -180 degrees, the gain is above 0 degrees. This means that this system is already unstable, and we need to degrade the phase or reduce it by around 7 dB at least to make it stable, and that's why this number is negative. So essentially we need to compare 0 with the gain of that frequency. And similarly, the frequency at which the gain becomes 0 is this one, and the phase is at this value lower than -180 degrees. Which is 18.5 degrees lower. We want always the phase to be higher than -180 degrees to make sure that the system is stable. In this case, the phase needs to be modified by 18.5 degrees at least, and increased by that value to be able to make a stable system. So you can see that gain margin and phase margin could both be positive and negative values, and with this we can find out at how much modification we need to incur into our system. So this was the main purpose of this tutorial, and I would leave the rest of the examples as an exercise to you guys. Please leave your comment below under the video if you have any questions.
Thank you for watching. Hit like and subscribe to the channel if you enjoyed this video.